Hi, this is Dr. Anthony Revis with SVSU General Chemistry 111, Chapter 2, Lecture 1 of Chapter 2, Atoms, Molecules, and Ions. The following topics will be covered, but not necessarily in this order. We'll take a look at early ideas of atomic theory, evolution of atomic theory, atomic structure and symbolism, that is, the symbols used, chemical formulas, the periodic table, molecular and ionic compounds, and chemical nomenclature. This slide shows you the periodic table. This is essentially the Bible for chemists. The periodic table was developed in about 1872. It really was a major breakthrough in understanding how to organize elements in a fashion that was very useful for predicting science and for carrying out chemical transformations. So, the periodic table is essentially what chemists and scientists look to when they want to understand some things about elements and how to use elements to carry out chemical transformations. Arrangement of the elements are by increasing atomic number. So each element on the periodic table has an atomic number. That's a small whole number. It's an exact number. Okay, it does not have any decimals. So the atomic number and the atomic mass increase from top to bottom. Okay? And the atomic number on the periodic table matches the number of protons in each of the elements. And we're going to learn this as we go through this chapter. It's also arranged with elements in groups with similar properties. So the elements in the groups have similar properties. And again, this is the arrangement of the elements on the periodic table, starting at 1 through 116. And actually, the periodic table has the slots for 118. And predictions about what those elements will be if discovered or somehow synthesized. This is where those elements would fit on the periodic table. The blank slots at 113, 115, and 118. Predictions about what they will look like are straightforward for us to make, and those elements have not been discovered, neither have they been synthesized. When we look at the periodic table, elements are arranged according to similar properties in vertical columns called groups. So the groups are the columns. You look at the columns, you'll know the groups. Elements in a column have similar properties, and that's the important take-home message about the groups. So if you look at group 1 through 18, you'll learn the numbers as we go, but they're arranged 1 through 18 columns. Column 1, elements have similar properties. 2 have similar properties. 3 and through 18. Periods are the horizontal rows. The periods are arranged in increasing atomic number, increasing atomic mass, increasing number of electrons in its atomic structure. And there's 7 periods on the periodic table. So, on the periodic table, let's recap. We have 18 groups with elements in those groups having similar properties. We have periods, which are the rows. We have 7 periods, and those are arranged according to increasing atomic number. Let's talk about the group numbers and periods. Group numbers, which identify the vertical columns of the periodic table, are written in 2 ways. There are 2 methods that they're written. One involves using alphabets. The letter A is used to represent elements 1A to 8A. And we'll look on the periodic table again to identify where these are. And the letter B for the transition elements. The transition elements are in the valley on the periodic table. So you locate the valley, you locate the periodic table. These will be the B groups. The A groups would be those elements above the valley. Okay? And they are 1A through 8A. So, one way to arrange them, the groups, is by the A's and the B's. The A's being those above the valley, on the hills, and in the valley would be the B's, the transition elements. And then we have the regular numbers 1 through 18. The A and B designation for the periodic table is the oldest designation. The 1 through 18 is a newer designation. In Gen Chem, I tend to use the 1 through 18 numbering for the groups. Analytical chemists tend to use the A and B, and there are certain properties associated with the A's that are different than those of the B's. So the B's, again, they have transition element, they have their transition elements, and they have certain properties related to being a transition element. One of those properties being the ability to have more than one charge, more than one positive charge. The A group have a stable charge, although there is the possibility for some of those to have a different charge. Okay? And there are many other properties related to being the A and the B, that the detail of which will be in some of the more advanced courses. So, for the most part in Gen Chem, you will hear me and others refer to them as 1 through 18, starting from left to right. And then the periods, you simply count down from top to bottom as the rows. Notice that in the periodic table, hydrogen tends to show up either on the far left or the far right. And there are very good reasons for that we will learn as you go through the course. Okay? So be aware, the very first row contains hydrogen. This periodic table shows you some other ways that we identify elements on the periodic table. We note that group 1A contains what's called the alkali metals. You now know that a group will have elements with similar properties. Hydrogen is not an alkali metal. Okay? But starting at row 2, which is period 2, we have the alkali metals. And then next to it, we have the alkali earth metals. They have similar properties. Both these groups form good bases with a reactive in water, and they form good hydroxide and other alkali bases. The alkali earth metals and the alkali metals. Then we have the transition elements, which is an area that I call the valley. That's 3 through 12. 3 through 12, or the B group. In this group, we have metals in this area capable of adopting more than one charge. The transition metals are used quite a bit in catalytic processes. Then we have a group shown in blue on this slide that really don't have a common name for these, but these are nonmetals, except actually not all of them are nonmetals, but several are nonmetals, and this is also where we have metals that are used in the electronic industry. Then group 17, the halogens, or group 7A. So these are the halogens. The halogens are diatomic by nature, meaning that they don't exist as a single element. They exist as a dimer of that element. For example, iodine is not I in its natural state, it is I2 in its natural state. Br is not Br in its natural state, it is Br2 in its natural state. That is one of the unique features of the halogens. They are diatomics. You will also learn other diatomics. And then we have the noble gases. The noble gases are exactly that. They are noble gases. They have what's called a full octet, meaning they have 8 electrons around it. They're perfectly happy being that way. They're extremely stable, and they wish not to combine with other elements in the periodic table. So for the most part, they sit on their throne and they are noble. So let's recap. On the periodic table, we have groups 1 through 18, or we have the A group, which are on the hilltops, and we have the B group, they're in the valleys. We also have periods, which are the rows, starting with 1, which is where hydrogen is located, along with helium is located. And then we have period 2, where we start the alkali metals and the alkali earth metals. We have the transition elements in the valleys. Then we have a group of elements that don't really have a common name, but you will learn some more specifics about that group, particularly the group of metalloids, which are used in the electronics industry. And then we have the halogens, which are group 17, which are diatomic species in their natural state. They exist as a dimer than as a single. And then we have the noble gases, which completes the octet rule. They prefer to have 8 electrons around them, other than helium, which has 2, but those 2 satisfy its thirst for electrons, or its need for electrons, and it's very stable. As we mentioned to you already, there is a special group of elements on the periodic table known as metalloids. That's shown in this slide in green. The metalloids follow along what's called the periodic table diagonal. These metals, these elements, are used really heavily in the electronic industry, of which silicon is one of the keys. Silicon is the metal in your cell phones and in your electronic devices. In the state of Michigan, silicon is manufactured out in Hemlock, Michigan, with Hemlock Semiconductor Corporation. And then you have these others along the green diagonal shown in this slide. The boron and arsenic being used as dopants in the electronics industry to bring about special electronic properties to your electronic device. And then you have the others. Shown in yellow are the non-metals. These are basically non-metallic materials. Then we have the blue area shown as metals. The periodic table is composed mostly of metals. There are more metals, far more metals on the periodic table than there are non-metals. The metals on the periodic table will typically undergo oxidation to form positive charges. Let's talk now about some of the properties of these metals, nonmetals, and metalloids. Most metals are shiny solids, such as copper, gold, and silver. Metals are also ductile, meaning they can be shaped into wires, which is one of their major uses of these metals, is to make into wires for electronic applications. They're malleable, meaning they can be hammered into flat sheets, and that happens a lot in metalworks areas where they will hammer the metal into some shape. All right. They're good conductors of electricity, which makes them very useful for electrical wiring. You can melt a metal at much higher temperature than non-metal. So you need a lot of heat to melt metals. They're solids at room temperature except for mercury. So metals will be solids at room temp except for mercury. They have higher density because the atoms, the molecules, are packed in very, very tightly, and they're very dense. Mercury, on the other hand, is an exception to that. It is a liquid at room temperature. Except for aluminum, the elements along the zigzag line are metalloids along the periodic staircase. These include the ones shown here, and we've talked about some of them already. Each of these metalloids have a unique application in the electronic industry. Again, with silicon being more so than any of the others. Silicon, boron, and arsenic are critical to the performance of your cell phone. These metalloids exhibit some properties typical of metals and some of nonmetals. So they are along that diagonal where the boundary between metals and nonmetals exists. Metalloids are better conductors of heat and electricity than nonmetals. Let me repeat that. Metalloids are better conductors of heat and electricity than nonmetals, but not as good as metals. That's important to note. As semiconductors, they're very useful because they can be modified as conductors or insulators. So they have the ability to function as a conductor or an insulator, and that is a unique property of metalloids, that ability to be either a conductor or an insulator. And that's an important feature depending on how they are modified. Nonmetals include elements such as hydrogen, carbon, nitrogen, oxygen, chlorine, and sulfur. Nonmetals are not especially shiny, they're not malleable, they're not ductile, and are poor conductors of heat and electricity. Typically, they have low melting points and low density, and those are some unique properties of nonmetals. This table summarizes the features that we've already talked about of these metals, nonmetals, and metalloids. Take a look at this table. You'd be wise to at least understand some of the principles. Most don't ask you to memorize the table as it exists. However, understanding and knowing the key properties that we've already discussed about each of these groups is an important concept in freshman chemistry. Therefore, taking time to memorize or learn these concepts about metals, nonmetals, and metalloids is very, very important. Knowing what the physical properties are typical. Knowing what physical properties are typical for the metals, nonmetals, and metalloids is a very important concept that we expect people who take Gen Chem to understand and be able to regurgitate and to verbalize. So now, let's start to understand a bit further what types of science went into developing the understanding of the principles that led to the periodic table. And many of these principles were not completely formulated until later years in chemistry. And so we're going to take a look at that to further understand it. What led to the science that's behind the periodic table and the science and the fundamentals that lead to understandings about molecules and matter. The Daltons atomic theory is the leading principle that we hold to with regard to understandings about molecules and atoms. That's why it's called the Daltons atomic theory. Let's talk about 4 important summary points from this theory. We will not go into an in-depth derivation of the theory, but instead the expectation is that we will summarize that and use that information as we go throughout the course. Let's take a look at the first principle that we learned. Elements are composed of extremely small particles called atoms. This is something most people know. That knowledge came from what we call the Dalton's atomic theory. So elements are composed of extremely small particles called atoms. All atoms of a given element are identical. They have the same size, mass, and chemical properties. The atoms of one element are different from the atoms, however, of all other elements. For example, the elements in carbon are different from the atoms in carbon are different from the atoms in nitrogen. But all the atoms within a carbon molecule are exactly the same. Compounds are composed of atoms of more than one element. That's because compounds are composed of more than one element. In any compound, the ratio of the number of atoms of any two of the elements present is either an integer or a small fraction. However, we don't use fractions in writing, we use small whole numbers. Now, in some mathematical derivations, you will see half numbers in these structures. The reason for those half numbers will be to help you understand the basic fundamental how these elements work together. Okay? But when we write our final equations, when we write our final compositions and compounds, it uses whole numbers. But again, keep in mind, and in fact in my presentation, you'll see some half numbers for some of these. That's simply to do the math by. That's it. It's to demonstrate what the math looks like. Okay? So keep that in mind. So, compounds are composed of whole numbers. Okay? A chemical reaction involves only the separation, combination, or rearrangement of atoms. It does not result in the creation or destruction. In other words, it allows them to be separated, combined, or rearranged, but it does not create nor destroy any of those. Matter cannot be created nor destroyed. Okay? That is a fundamental principle of science. You cannot destroy matter, neither can you create matter. You can only transform it. That is the law of the conservation of matter and energy. That you can't create it, you can't destroy it. Conservation of matter, the law of conservation of matter, teaches us that. So chemical reactions can only separate, combine, or rearrange atoms. It cannot create them, neither can it destroy them. So what does that mean in a practical sense? What does the Dalton atomic theory really mean, and where does it get us? Well, it helps us understand why and how atoms combine with atoms to form compounds, how elements combine with elements to form compounds, how matter combines with matter to form new forms of matter. It doesn't create them, but it transforms one form of matter into another form of matter. And we show you here an example of carbon and oxygen combining. Okay? In the first one, we can combine one atom, one molecule of carbon with one molecule of oxygen to form one molecule of carbon monoxide. We can also take 2 moles of oxygen, 2 atoms of oxygen, and one atom of carbon and form carbon dioxide. So the Dalton atomic theory allows us to understand why these reactions can occur and how these atoms can combine. That is the bottom line of what Dalton's atomic theory helps us understand. And what does that mean? What it means is that elements may combine in a variety of integer ratios to form multiple compounds, each with a different property. That's what the theory helps us to understand. Okay? That we can have different ratios of these atoms combining to form different compounds. Okay? For example, iron can combine with oxygen and give us Fe3O4, or it can combine to give us Fe2O3. One form is a magnet. The other form is rust. And that's the important principle that we get to take home from this. Okay? One form is a magnet and the other form is rust. So, because it can combine in those different ratios, we can get compounds with different properties. Much of this occurs naturally in nature. We dig it out of the ground, and that's when we discover what it's composed of. And having done this, people like Dalton, some of the earlier scientists, really discovered these combinations and really start to understand what was happening at the atomic level. When we think about then the Dalton theory, we can now relate that to molecules and why molecules can form, or why molecules form. And what's a molecule? A molecule or compound is an aggregation of two or more atoms in a definite arrangement held together by chemical forces. That gives us molecules, and these molecules, from these molecules we form compounds. From compounds we form other types of materials that we get to enjoy in our everyday living. Okay? Now, a diatomic molecule contains only two atoms, and that's important to understand what a diatomic molecule is. Now, you're going to hear the word diatomic used somewhat interchangeably. If it's more than one element together, that is a diatomic molecule. For example, HCl is a combination of hydrogen and chloride, therefore it is a diatomic, two atoms together. Carbon and oxygen is a diatomic, two atoms together, one carbon, one oxygen. Now, but keep in mind, there are also these natural states of diatomics, which is hydrogen gas, nitrogen gas, and oxygen gas, and all of the group 17. In CHEM, this can be confusing because more times than not, when professors are talking about diatomics, they will be talking about group 17. So you want to be aware of that. But as a formal definition, any combination of two elements is a diatomic molecule. The naturally occurring diatomics, or the natural state diatomics, are HNO and group 17. So let me say it real clearly. Two atoms together is a diatomic. But there are also natural occurring diatomics, and those are hydrogen, nitrogen, oxygen, and group 17. Then you have the polyatomics, meaning more than two, essentially, is what the polyatomics will refer to. So we show you some examples of the polyatomics here. Ozone, which we know is in the stratosphere, and it protects the Earth from UV rays, UVC, from coming through, and it also helps warm the Earth. Then we have these other polyatomics, of which there are too many to name at this time. So how do we know they're really atoms? How do we know that what Dalton and others were talking about was really true? Well, experiments were done by Rutherford that really helped to better define and really identify the subatomic particles that theory said must be there. Rutherford ran an experiment, and the result of the experiment was that he discovered the subatomic particles that were within the atom using a light scattering device. You can go out and Google and watch many videos on this. At the end of the day, what he discovered was that there was this movement of subatomic particles. And he discovered that an alpha particle had a velocity of 1.4 times 10 to the 7 meter per second. That's approximately 5% the speed of light. So he knew something was going on here. And what he found and discovered from this is that there were these protons, electrons, neutrons, these subatomic particles that formed atoms. So an atom's positive charge is concentrated in the nucleus. That was one of the results of this study, and one of the results they found. The positive charge in atoms was in the nucleus. Also discovered was a proton has an opposite charge of an electron. That a proton is positive, and therefore the proton must be located in the nucleus, since the concentration of positive charges in the atom is in the nucleus. The electrons, on the other hand, which had the opposite negative charge, were located in the outer ring area of the atom. Also discovered that this atom had mass. We'll talk more about that mass. And what we further discovered was that the bulk of that mass was in the nucleus. And he further found that that mass was composed of protons and neutrons. Long story to tell you that protons and neutrons make up the nucleus of atoms and is surrounded by electrons. That is the take-home message. And that the mass of the atom is contained within the proton and the neutron, and there's less mass in the electron, to the extent that in basic calculations, the mass of the electron is ignored. Okay? So what else can we say about the atom then? An element of the periodic table is an atom. Okay? That's one of the things we can say about it. An element of the periodic table is an atom. And in fact, you will hear the term atom and element and actually molecule often used interchangeably. Understand the context of the conversation or the discussion is very important to understanding how these terms are used. This is the language of chemistry that you will get accustomed to as we go through the course. Also discover that the atom is electrically neutral. It does not have a charge. Its net charge is 0. It also has an equal number of protons and electrons as the neutral atom. That's important. So the elements on the periodic table are neutral. Since they are neutral, the number of protons equals the number of electrons. And that's important to note. Neutral atoms, the protons and electrons are always equal. And so here we show you what the mass looks like for these. We note that the mass of the electron is 10 to the minus 28, which is much smaller than 10 to the minus 24 for the protons and the neutrons. And that's important to know. Okay? Therefore, the mass of an atom is attributed to its protons and its neutrons. It's also been found and discovered that the electrons have a charge and the protons have a charge, but the neutrons do not. Therefore, the charge for the electron assigned to the value -1. The charge of a proton is assigned a value of +1. That is the charge unit. Okay? So, it's important that you understand the principles related to this table. Again, electrons have very low mass. Protons and neutrons are the key subatomic particles that contribute to mass. The charge of electrons, -1. Charge of protons, +1. No charge on the neutrons. Another way of looking at the mass is by its AMU. The AMU for protons is 1.0072 AMU with a charge of +1. Neutrons has a mass of 1.0087, slightly heavier than a proton, and no charge. Electrons, has a very small AMU mass, 0.00055 AMU, atomic mass units. You'll learn about the atomic mass units in this lecture as well. The charge of electrons, -1. When we consider matter, atoms are pure substance. Atoms make up molecules that make up compounds and elements that make up matter. And that's important to be aware of. Okay? So an atom is a pure substance, is the bottom line take-home point from this slide. Now, when we talk about these subatomic particles, we talk about them with regard to their atomic number, the mass number, and the isotopes. And this is where you really want to pay attention to the exact terms that are used, because some of the terms are really, really close in what they sound like. And we will do our best to help you differentiate those. Okay? And the symbols used for them. The atomic number, which is called Z, is the number of protons in the nucleus. That number, the atomic number, is the small whole number on the periodic table for each element. Each element has a small whole number, which is its atomic number. That atomic number does not change for the elements. It is always equal to the number of protons. Therefore, the number of protons for each element do not change. The protons for carbon, what it is for carbon, is 6, and it stays that way. For nitrogen, it's 7. It stays that way. So that number of 7 is the atomic number for nitrogen, if you look at the periodic table, and that is also the number of protons. The mass number, which is different from the atomic mass unit, and you want to know that is different. The mass number equals the number of protons plus the number of neutrons. The mass number is not the decimal number on the periodic table, and it is not reported by rounding off the number on the periodic table. That is a very common mistake that some listening to this video will make, but that will be incorrect. It is not the rounded off value of that number on the periodic table. So when you're asked for a mass number, do not look at the periodic table for the answer. Mass number is either given or calculated, and it will be a whole number. Okay? Isotopes are atoms of the same element, which we call X, with different numbers of neutrons in it. So if it has different numbers of neutrons, then elements can have different mass number. Okay? That's important to note. It's called the isotopic effect, that you only have one atomic number, which means you only have a set number of protons that never change, but you can have variability in the number of neutrons. That is a point that you must hang on to. We show you examples of this in terms of hydrogen. Hydrogen has an atomic number 1, which is shown on the bottom of the element, and on the top is the mass number. It also has a mass number of 2, which is called deuterium, and then a mass number 3, which is tritium. But the number of protons never change on the bottom. That's important to note. So you can have different isotopes, different mass numbers, but only one value for the protons. Also show you for uranium as well. Uranium 92, 92 being the atomic number, which equals the number of protons. But the mass number is different. In other words, we always make up for the mass number difference by the number of neutrons. Let me repeat myself. The number of protons will always stay the same. The mass numbers will change. The change in the mass number will be related to the neutrons, to a change in the number of neutrons. So anytime we have an isotopic effect, meaning the mass numbers are different, that is neutrons. It is not protons. It is not electrons. We show you also an insert here of the abbreviation that you will see in this course, and you'll see in many courses, and hopefully these will help it to settle down and some things will make some sense. Okay? But it's important to note that the mass number is not the number on the periodic table that you see as the decimal for molar mass. That is not the value. So let's talk further about the atomic number. The atomic number is specific then for each element and the same for all atoms of that element. It's equal to the number of protons in the atom. Appears as a symbol of the element. So the atomic number, you will see it many times over the top of the number on the periodic table or in the left-hand corner of the periodic table. But when we write it for isotopes, it's usually written on the bottom of the symbol. So, the atomic number. And then we have the chemical symbol as well. Okay? Let's talk some more about that mass number. The mass number equals protons plus neutrons. That's it. It is not the rounded value from the molar mass that's on the periodic table. It represents the number of particles in the nucleus. So that's how many particles you have in the nucleus. So you know the mass number, you know how many particles are in the nucleus. And the nucleus is where the protons and neutrons are. That is where the positive center of the atom is. And then it's surrounded by the electrons. The mass number, okay, is equal to the protons plus the number of those neutrons in the nucleus. It does not appear on the periodic table because it applies to a single atom only. It is not the AMU or gram per mole value. We cannot reiterate that enough. And you will see here on this slide, atomic mass unit is not the mass number. Occasionally, however, you will hear the mass number referred to as atomic mass. Okay, so be aware of that. All right, and there's history behind why that's the case. Suffice it to say, in your studies of Gen Chem, atomic mass units are not the same as the mass number. The atomic mass unit, which is on the periodic table, has a decimal value, it's on the periodic table, is equivalent to the molar mass or the AMU. But the mass number is a whole number. It deals with the isotope. It deals with protons plus neutrons. So in any discussion of subatomic particles, be sure that your mass number is a whole number, but do not get that value from the periodic table. It's either given or it's calculated. And the calculation would be from protons and neutrons. Neutrons come from the mass number. We calculate the number of neutrons in an atom from its mass number and atomic number. Mass number minus atomic number equals number of neutrons. For example, potassium has a mass number of 39. That's given to you. That's looked up on a table, not the periodic table. And its atomic number of 19. Therefore, to find the number of neutrons, subtract the atomic number from the mass number, and we get 20 neutrons for this example of potassium, because it has a mass number of 39. It is possible that potassium might have some other mass number. You would do the calculation the same way to obtain the number of neutrons. On the other hand, if you know the number of neutrons for an element, you will look at the periodic table for that element. You would obtain its atomic number, which equals the protons. You would add the protons and the neutrons to get the mass number. Under no condition should you round the number on the periodic table. These are some more examples. Oxygen 8, which is the atomic number, which means it has 8 protons. And since it's neutral, it has 8 electrons. All neutral atoms, all neutral elements, have the same number of protons and electrons. That's why it's neutral. The neutrons will vary. Notice in each of these examples, the protons and electrons are exactly the same, but the neutrons are different. The neutrons are different for each of these. Therefore, if you add the neutrons and protons, you'll get the mass number shown at the top of each of these elements. We show you an example here with just carbon, where it's carbon 12, carbon 13, carbon 14. And the reason it's carbon 12, 13, 14 is because there is a difference in the neutrons, not the protons, not the electrons. That's critical to hold on to. This is a classic example of a problem that you might see on a Gen Chem exam. You certainly might see it on an ACS exam, where the isotopic value change, the mass number change, and occasionally you'll be tempted to change the protons and electrons. The protons and electrons do not change because the protons never change. Never change the protons. They are always equal to the atomic number. And here, just for fun, we show you a table that we will not fill in during this lecture, but we show it to you here, and we show you the results to play with and hopefully to reinforce the concept. So you do well to play with this table, play with a blank one, and to see how it matches with the one that's not blank. The bottom line is the Dalton theory allowed us to understand that there are protons, neutrons, and electrons that make up subatomic particles that are combined to give us the atom. Protons and neutrons form the nucleus, which contains a positive center. Electrons are surrounding the nucleus to give you the negative. The positive and the negative gives you neutral. The mass is due to the neutrons and protons. So that ends it for Lecture 1 of Chapter 2, Atoms and Molecules.